Okay, I'm going to show you guys how to do monohybrid test cross, which you probably already know how to do, but I'm going to summarize it up to make sure that you know what's expected of you, and then we're going to use these monohybrid crosses to show you how to do the shortcut for dihybrid crosses to make life easier instead of having to do a big Punnet square. And we're going to use genes that show complete dominance for a flower color. This is not a real flower. We're going to take a plant that has red flowers that are dominant and blue flowers that are recessive. And if you do a cross between a true breeding red flowered plant, which means that plant is homozygous dominant, and you cross it with a true breeding blue plant, which means it's homozygous recessive, you're going to get a cross to where the parent of the red plant offers alleles and its gametes there and here, and the blue plant, sorry for that noise, it's the headphone, offers alleles here in its gametes and here for its gametes. And when you do a test cross, you simply combine the gametes. Boop, boop. We're going to make this a little easier. Put that there, and this is going to be big A, that's going to be big A, that will be big A, and that one will be big A. So all the offspring are going to be heterozygous, but they will still have red flowers. So another cross we're going to do, well, delete that part. And so we come down here and we see that the probability for having a homozygous dominant is 0. Probability for having heterozygous, 100%. And homozygous recessive, 0. If you didn't see that, I typed here. And then I'm going to show you the probability of being dominant, 100%. Recessive, 0%. So when you cross two homozygous parents, one being homozygous dominant, one homozygous recessive, you get all heterozygous offspring. But what happens if you do a cross between those heterozygous offspring? No, that's not inbreeding. Well, yeah, it is, but it's flowers, plants. We're going to go down here. We're going to show you that the offspring from above were heterozygous right here, and they were all red. And we're going to do the test cross between these two heterozygous. And when we do that, we see that... I'm listening. Siri, hush up. Go away. I don't know why she came on. When we do that, we see that the gametes of both parents offered are the same because they're both heterozygous. And when we do the cross, this probability of having offspring homozygous dominant, we'll have to use the rule of addition to figure that out. Big A, and little a. So now what we're going to do is come down here to genotype probability, and we're going to count out of 4 how many are going to be homozygous dominant. And that equals 0.25, or 1/4. How many are heterozygous? Well, we're going to use the rule of addition. There's 1/4 plus 1/4 gives you 1/2. And homozygous recessive, 0.25. So out of that, how many of these offspring are going to be red? Well, we come over here, get rid of that, get rid of that, and we see to be red you have to have at least a dominant A allele. Red. There we go. So use the rule of addition. That's 1/4 plus 1/2 gives you 3/4. And recessive, 1/4. So now we have a 3-to-1 ratio between dominant and recessive phenotypes, and a 1/2-to-1 ratio of genotypes. 1/4, 2/4, 1/4. Now let's do another test cross between homozygous dominant red with a heterozygous red. And you'll probably predict that all of the offspring should be red. But what about the genotypes? AA, AA, big A, little a, big A, little a. What's the probability, of getting offspring that are homozygous dominant? We look here, and we see 2 out of 4. So we come down here, and we say 1/2. How many are heterozygous? 1/2. All these should add up to 1, by the way. How many homozygous recessive? 0. How many are dominant? All of them. How many recessive phenotype? None of them. But we see, and this will make sense later, is you have a 1-to-1 ratio of genotypes and no ratio. All the offspring are going to have dominant phenotype. They're all going to be red flowers. Now let's do a cross between a heterozygous red flower plant with a true breeding blue flowered plant. And if you haven't realized yet, the recessive phenotype is always true breeding. They're always homozygous. For this one, these right here are blue, little a, little a. And if we cross a heterozygous red with a homozygous blue, which again, redundant, homozygous blue, you have to be homozygous to have the recessive phenotype, we're going to figure out the genotype ratio. So if big A, little a, big A, little a, oh, sorry, I know, you saw that, big A, oh, excuse me, little a, big A, little a, little a, little a. And now, what's happened is, we have half the offspring are heterozygous red, half the offspring are homozygous recessive or blue. So we come down here and we type that in. How many are homozygous dominant? None, because both parents must have a dominant allele to be homozygous dominant. So we'll put 0. How many are heterozygous? Well, the rule of addition. 1/4 plus 1/4 gives you 1/2. And how many are homozygous recessive? 1/4 and 1/4 is 1/2. So half of the offspring are homozygous dominant, half the offspring are homozygous recessive. Oh, I know, I said homozygous dominant. Half the offspring are heterozygous, and half the offspring are homozygous recessive. And that means that how many are red? Half of them. How many are blue? Half. So if this is confusing, go back in the video and play it over. However, if this makes a little sense, I've summarized it up here on this table, and all this will be in the Dropbox. Well, it'll be on the website. So here we go. This shows you, I'm going to highlight these. All right, what this is showing you is something that I expect all students to have somewhat memorized, are the ratios or probabilities. So what I'm showing you here is when you cross 2 homozygous individuals, if you cross 2 individuals that one of them is homozygous dominant for a gene and one is homorecessive for a gene, all the offspring, that is incorrect. That is 1. All the offspring will be heterozygous. And all the offspring are going to be dominant. if you cross two individuals that are both heterozygous for a particular trait, you get the ratio of 1, 2 to 1 for genotype, and you get 3 to 1 for phenotype. So these are the numbers to remember based on these crosses. And if you cross a homozygous dominant with a heterozygous, you get, this is not right. So when you cross a homozygous dominant with a heterozygous, you get a genotype ratio of 1 to 1, and you get a phenotype ratio of just 1. All of them are dominant. But if you cross homozygous recessive with a heterozygous, you get a 1 to 1 ratio of genotypes, and you get a 1 to 1 ratio of phenotypes. So I hope all that monohybrid cross wasn't too confusing. So what I did was I created a table to summarize. And what this table is showing is if you know the genotypes of the parents for a monohybrid cross, and you know that the gene that you're doing a test cross with shows normal complete dominance, meaning the dominant allele is in the organism's genotype, they will express the dominant trait. And the only way to show the recessive trait is you are homozygous recessive. And also remember that true breeding organisms are homozygous for a particular gene. And that means recessive phenotype individuals are true breeding for that gene for recessive. And homozygous dominant individuals would be considered true breeding for that trait. So let's summarize. If you have two true breeding parents, one for the dominant trait and one for the recessive trait, and they do the test cross, all the offsprings are going to have heterozygous genotype, and they're all going to have the dominant phenotype. If you cross two individuals that are heterozygous, meaning big A, little a, and they're both showing the dominant trait or phenotype, the result will be a 1-2 to 1 ratio of homozygous dominant, heterozygous, homozygous recessive, or a 3 to 1 ratio for phenotype. And these fractions or probabilities are what you're going to use when I show you the shortcut. If you have an individual that is homozygous dominant and an individual is heterozygous, you're going to get a 1 to 1 genotype ratio, and all the offspring will be dominant. And if you have an individual that is true breeding recessive with a heterozygous dominant, you'll get a 1 to 1 genotype ratio like above. However, you'll have a 1 to 1 phenotype ratio. And we're going to use this information on doing a dihybrid test cross and not using the 4x4 Punnet square. Let's try that. So here we have, we're going to do an example. The P generation is where we crossed a true breeding red flowered with short petal plants, long petal plants, crossing with true breeding blue flowered short petaled plants. Well, their flowers are that color and the petal lengths are that colors. And these are made up. I don't know if this works in a particular species of plant, but we're just using this for demonstration. And we're going to refer to this table up here, this one. We're going to refer to that one in doing these crosses, and hopefully you remember this. And we're going to treat each gene independently, and we're going to use the rule of multiplication as well as the rule of addition in doing a shortcut. So let me bring you over here to show you that if you have two parents that are heterozygous, right here, I'll just type it, big A, big B, little b, crossing with big A, big B, little b. Hopefully you know now to set up their gametes, which are created during meiosis. We're going to put the gametes for each parent up here. So we're going to take this parent and we're going to do something called the FOIL method. And this is the long way of doing it. When you have a gamete, all gametes must have each gene represented. So that means each gene must be represented in the gamete. So that means this parent could have big A and a big B. And don't forget the little b. That means big A, little b. But don't forget the little a and the little a and the big B. And then the little a, little b. And as you probably figured out, the same goes for this parent. And it's simply the same thing. So I'm going to copy, and then there we go. That worked. And then you'll see that if we do the long way, this is AABB, 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 and then AABB, BB, little a, big B, little b, little a, little a, little a, b, little b. Bam. And so that means if we sit there and count, we've got to figure out how many of the offspring are red, flowered, and long petals. And that means red, long. And then how many are red, short, how many have blue petals that are long, and how many have blue petals that are short. So we're going to use the rule of addition. We're going to count how many are red and long. Well, to be red and long, you have to have a big A and a big B. So how many are big A, big B? 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is 9/16. We're going to highlight those that are 9/16. Now, how many are red and short? 1, 2, 3. Let's highlight those. So that means 3/16 of those are red and short. How many are blue? That's 3/16. And how many are short and blue? 1/16. So now we have a 9, 3 to 3 to 1 at a 16 ratio. That takes a while, as you see, to set up. So we're going to do the same thing, but we're going to use a shortcut, and we're going to use the rule of multiplication. And then we're going to be referring to a monohybrid cross, where both parents are heterozygous for a particular gene. And so if you recall, if you cross two individuals that are heterozygous for a particular gene, you get a 3 to 1 ratio of dominant to recessive phenotype. Let's do it. So this side is referring to color phenotype. This side is referring to petal length phenotype. This is the test cross we are doing, like we did before, and we're going to do the shortcut. And these genes do something that Mendel had observed called independent assortment, where the gene for color, A, is independent where the gene for petal length, B, goes. So we're going to take two parents that are heterozygous red and long petals and cross them. And we're going to look at each gene individually. So if you cross a red heterozygous with a red heterozygous, what's the probability that you're going to get red offspring? 3/4. So we're going to enter 3/4. So therefore, what's the probability of having blue? 1/4. And we're going to look at petal length. If both parents are heterozygous for petals, what's the probability of having long petals? 3/4. Short petals? 1/4. Great. Now, we're going to take these probabilities and multiply them. Rule of multiplication. So here, what's the probability of getting red individuals? 3/4. So I'm going to hit equals 3/4, and then we'll multiply that by probability of having long petals, 3/4. When you multiply that out, it's 3/16. So what I did was I multiplied this by that, and that goes right there. So what do you think is going to happen for red and short? Well, what's the probability of getting red? 3/4 and short petals, 1/4. So I'll hit equals this times this. Enter. 3/16. So and that goes there. Now blue and long right here. What's the probability of getting blue? 1/4. And what's the probability of getting long petals? 3/4. This equals blue times long. 3/16. So I did this. Blue and long goes there. Thank you. And what about blue and short? Well, that equals blue times short equals 1/16. And now, as you see, we get a 9, 3 to 3 to 1 ratio right here. And I'll draw it in fancy, sparkly colors.